Okay, guys, so today we're going to continue with chapter 6, inner product, and mostly today I'm going to talk about orthogonality. What does it mean two vectors in any vector space are orthogonal? So let me start by a very important inequality for inner product vector spaces, the so-called Cauchy-Schwarz inequality. We're not going to prove it here, but the proof is in the book if you want to read it. It's not that complicated, but it's really a trick. So that's the so-called Cauchy-Schwarz inequality. So assume I have an inner product vector space. So I'm going to call capital V a vector space, and inside capital V I have an inner product. So this one, an inner product vector space. The so-called Cauchy-Schwarz inequality is the following. The absolute value of the inner product of U with V, remember the range of the inner product, so that means the result of an inner product is always a real number, So inner product acts on two vectors, that is the input, and the output is going to give you a real number. So the Cauchy-Schwarz inequality tells you that in absolute value, this real number is always less or equal to the norm of U times the norm of V. And this is the so-called Cauchy-Schwarz inequality. Okay. Now, using this Cauchy-Schwarz inequality, I'm going to define the so-called cosine of the angle between two vector U and V. And let me tell you something. In this chapter, we are taking many terminology, using terminology that you have seen before in the Euclidean geometry, the geometry of the plane. So you will see that I'm talking about cosine of angle between two vectors. Also, those two vectors, they don't have to be really the only usual vector that you know in Rn. Could be matrices, could be polynomial. So it's a little bit tricky how to imagine what is angle between polynomials and stuff. Has no geometric interpretation. We are just taking the terminology of the geometry and putting it for general context. So, but we are keeping the same type of terminology. However, every word that we are using here is motivated by something. So, for example, now I'm going to talk for you about cosine of the angle of two vectors, and you will see how this is motivated by this Cauchy-Schwarz inequality, and the cosine will make sense for you. Okay, so now let me assume U and V are non-zero vectors in capital V. So basically I'm saying I don't want U to be the O vector of V, and also V is not the O vector of V. Okay, I just stay away from the trivial case, the O vector. Okay, then by the Cauchy-Schwarz inequality, Cauchy-Schwarz inequality, we have, so now look to this inequality. Since U and V are not the O vector, so norm of U is not 0 and the norm of V is not equal to 0. So I'm going to take this inequality and I'm going to divide both sides of this inequality by the norm of U, norm of V. Divide both sides by norm of U, norm of V. Then we will obtain the following. So absolute value of U, V, divided by norm of U times norm of V is less or equal to 1. Okay? So now the norm is always positive. So I can extend this absolute value to the whole thing. And I say the absolute value of the inner product UV divided by norm of U, norm of V is less or equal to 1. Now in calculus 1, you know, if I have absolute value of x less or equal to 1, this is equivalent to say x is between -1 and 1. So I'm going to write it this. So minus 1 is less or equal to inner product uv divided by norm of u, norm of v, less or equal to 1. Okay. Now I know that this quantity that is norm of the inner product uv divided by norm of u, norm of v, is always between minus 1 and 1. This is because of Cauchy-Schwarz inequality. So this quantity is always between minus 1 and 1. Well, that reminds me the cosine. The cosine, you know that the value of cosine is always between minus 1 and 1. And so this quantity here, I'm going to call it the cosine of the angle between u and v. So it has a meaning. So we call it cosine. So I don't want it's exactly, we call it the cosine because I know that this is always between minus 1 and 1. So I take this quantity and I'm going to call it cosine. So this quantity here, I'm going to call the cosine theta, and I'm going to introduce the following definition. We define the cosine of the angle cosine of the angle between two vectors u and v by cosine theta is u v divided by norm of u, norm of v. And if you go to the Euclidean geometry, if I have u here, v here, then this definition corresponds exactly to what you see here, the angle theta between u and v. Now let me say something important here. When you have angle, always we take the angle theta to be between 0 and pi. So when I have vectors, you don't read the angle theta to be this one, not this one. We read it only, it's between, we take it between 0 and pi. Okay, so even if vectors like this is u, here is v, okay, I don't read this one to be the angle theta. No, this is the angle theta. Theta is, we take it always between 0 and pi. So now here, if you have cosine theta is this, then if you want to compute theta, well, you take the cosine inverse. So, okay, so let's write it. Theta is going to be cosine inverse of this quantity uv, norm of u, norm of v. And remember, always we take the theta between 0 and pi. Okay, so no need for this. The angle theta always between 0 and pi. So that is the notion of cosine of the angle between two vector space. I repeat, when you are in Rn or in R2, like the xy plane, this exactly corresponds to what you see here. You draw two vectors and you see the angle between them. This is exactly like this. But when you are talking about matrices, polynomial, definitely it has other meaning, not geometric one, that the conceptual that you see it really. I mean, you visualize. Here you see, you visualize things, but you tell me, for example, angle between polynomial or angle between matrices is very hard to visualize. However, we are taking, as I said, we are taking the terminology of the geometry and we are applying in general context, in the context of any vector space. Okay, but the motivation is really comes from the motivation that you have seen before in the real Euclidean geometry, xy planes. Okay, now, so this is definition. It's a definition, so you cannot discuss it. Just a definition. This is what we call the cosine of the angle between two vectors. Okay, now we go to the orthogonality. So, because now we can motivate with the word orthogonality. You know, when we say orthogonal, that means perpendicular. They are orthogonal. Vectors are orthogonal to each other. That means they are perpendicular to each other. But we don't use the word perpendicular when we are dealing, when we deal with vector and then in vector space. Vectors we say orthogonal. We don't say vectors are perpendicular. Okay, for line, yes, we use the word perpendicular, but for vectors we say they are orthogonal. Now for us, vectors are orthogonal if and only if, this is the definition, their inner product is equal to 0. So two vectors are said to be orthogonal if their inner product is equal to 0. Now coming back here, why we use the word here, the motivation why you use the word orthogonal. Now when the inner product is equal to 0, the cosine will be 0. So if the cosine is equal to 0 and your angle is between 0 and pi, that means the theta must be pi over 2. And pi over 2, that tells you that they are orthogonal to each other. This is what we took from geometry, the Euclidean geometry. We took this terminology. So I repeat, if the inner product is equal to 0, the cosine will be equal to 0. Cosine of theta is equal to 0, and theta is between 0 and pi over 2. That tells you theta is equal to pi over 2. And that means your vectors, if I draw them in xy plane, so if I'm, for example, in the xy plane, that means I'm in R2, you will see u like this and the v like this. So they are really orthogonal to each other. Okay, so let's write this second definition. Two vectors u and v in an inner product vector space are said to be orthogonal if and only if the inner product uv is equal to 0. Okay, so in this case, the cosine of the angle between them, I come back here, put the inner product is equal to 0, and that means the theta is equal to pi over 2. Okay, so this is really the motivation of the word why we use this terminology, orthogonal to each other, because the angle between them will be in this case equal to pi over 2. Okay, now remark, very simple remark. So inside this vector space, the O vector is orthogonal to all vectors in V, because if I take the inner product, O vector with U will be equal 0 for all U in V. So the O vector is orthogonal to any other vector inside your vector inner product vector space. Very simple, because the inner product of the O vector with any vector in V is equal to 0. So the O vector, by this definition, O vector is orthogonal to any other vector in the vector space. Okay. Another thing important here. Okay. Let's let me call it Pythagorean Theorem. Okay. Assume we are inside an inner product vector space, so exactly like this, and I have two vectors that are orthogonal to each other, and I'm gonna now compute their sum, norm of their sum, square. Okay, so I'm gonna assume U and V are orthogonal. That means by this definition, the inner product U with V is equal to 0. Okay, then I'm going to compute the norm of u plus v all squared. By definition, this is the inner product u plus v with u plus v. Now I use the property of the inner product, linear in the first component, second component, and then you just write it. It's u plus u v plus v u plus v v. So it's gonna be equal norm of u squared plus, so it is symmetric, so I can write it 2 times uv plus norm of v squared. Okay. Now here, our assumption is that u and v are orthogonal to each other, so this quantity here is equal to 0. So I end up having thus the norm of uv all squared, it's equal norm of u squared plus norm of v squared. And this is the so-called generalized Pythagorean theorem. So we prove the Pythagorean theorem for any inner product vector space. Remember this one, whenever u is orthogonal, whenever u is orthogonal to v. If you draw it in R2, that means the xy plane, then I have a vector u. This is a vector u. This is a vector v. You have u is orthogonal to v. When I compute u plus v, what is u plus v? Well, here is u plus v. Okay, so I have this one is u plus v. And now I compute the norm of u plus v squared is equal this squared, and this, remember, this is what? This is a v. This is v. So we have the norm of u plus v squared, it's equal u squared plus v squared. So this is what you know from high school. This is a Pythagorean theorem in the right triangle. So you have here the right triangle, and you know that the hypotenuse squared is equal to the sum of the square of the other sides. So, but here we did it for any general inner product vector space. So u and v, they could be matrices, they could be polynomial, they could be function, any general inner product vector space. So very simple calculation. You just use the definition of the norm, you write it down, and use this definition of being orthogonal to each other, and this becomes trivial. But if you draw this in R2, the xy plane, this is exactly what we are talking about here. This is exactly this one. Okay. Another important thing, the so-called triangle inequality. Triangle inequality. Okay. Let's see what is this triangle inequality. Okay. Now, I go back to this written here. So, for any two vectors u and v, we have, I'm not going to assume u and v to be orthogonal here to each other. Just, I'm going to rewrite this now, what I wrote here. I have the norm of u plus v all squared is equal norm of u squared plus 2 times the inner product uv plus the norm of v squared. I just computed things here. So we don't need the u and v to be orthogonal. So just any two vectors u and v. Now, I want to use Cauchy-Schwarz inequality here. I know that x, for any real x is always less or equal to absolute value of x. This is a fact. X is always less or equal to absolute value of x. So I'm going to say this is less or equal to norm of u squared plus 2 times absolute value of uv plus norm of v squared. Okay? Because the real number inner product uv, it is a real number, is always less or equal to its absolute value. Okay, now, so that is easy trick here. I put this one less or equal to its absolute value. Now I would like to use the Cauchy-Schwarz inequality. It tells me the absolute value of the inner product is less or equal to the product of the norm. So I'm going to say this is less or equal to norm of u squared plus 2 times norm of u times norm of v plus norm of v squared. Now, obviously, what I'm seeing down here is the perfect square. So this is equal now norm of u plus norm of v all squared, the perfect square. And so basically what did I prove here? I proved to you that for any two vectors in an inner product vector space, the norm of the square is less or equal to the sum of the norms all squared. So now I can take the square root on both sides, hence we obtain the following. Norm of u plus v is always less or equal norm of u plus norm of v. And this is the so-called triangular equality. Now, in the xy plane, if you are dealing with the normal Euclidean geometry, basically what you are saying, here is a vector u, here is a vector v, here is u plus v, so I construct u plus v. This is u plus v, and you are saying that u plus v is less than the norm of u, because this is u, plus norm of v. Obviously, to go from here to here is shorter than going from here to here plus from here to here. That is obvious. So this is exactly what we are saying basically in the triangle inequality when you draw it in the xy planes. That means the normal Euclidean geometry. Saying this length is less than this length plus this length, which is obvious. Okay, so that is what we call the triangle inequality. The same happened for the distance. You can write it again for the distance. Okay, so if I have distance from u to v is always less than the distance from u to z plus distance from z, for example, to v. You can do it with the distance. Okay, it's exactly the same proof. Okay, now another important thing here. I'm going to introduce the so-called orthogonal complement of a given subspace or vector space. Okay, so definition. Okay, so I'm assuming I'm inside a big inner product vector space. Okay, so let W be a subspace of an inner product vector space I call it V with its inner product. And I assume I have a subspace inside, okay? We define the orthogonal complement of W denoted this we denote it like this. We put W and we put perp here. The sign perpendicular, you see? So denoted, so this we define the orthogonal complement of W denoted to be the set of all vectors in V that are orthogonal to all vectors in W. So in other words, here is the definition. W orthogonal complement. So it's the set of U in V such that the inner product UV is equal to 0 for all V in W. Okay? For all V in W. So you take the vectors that are orthogonal to all the vectors in W. So you take vectors that are orthogonal, but it has, every time you pick up a vector, it has to be orthogonal to all the vectors in W. You collect those vectors together and you form the so-called the orthogonal complement, the orthogonal complement of W. So any vector in the orthogonal complement is orthogonal to all the vectors in W. I repeat, any vector in the orthogonal complement is orthogonal to all the vectors in W. Okay, now, there is a simple fact, easy to show. W orthogonal, this orthogonal complement, is a subspace of V. So here, W, the orthogonal complement, is a subspace of V. In fact, why this is true? In fact, the orthogonal complement is not empty because the O vector is in W perp. Look what I wrote here. The O vector is orthogonal to all the vectors in V. So in other words, the O vector is orthogonal to every vector in W. In particular, so because this O vector is orthogonal to all the vectors in V, in particular, the O vector is orthogonal to all the vectors in W. So the O vector is in the orthogonal complement. So the orthogonal complement is not empty. Now I'm going to take two vectors in the orthogonal complement, and I'm going to show you that the orthogonal complement is closed under addition and multiplication by scalar. So I'm going to say let U1 and U2 be in W orthogonal, and let lambda be in R. Then for any vector V in W, we have so I'm going to compute the inner product U1 plus lambda U2 with a random vector V in W. Random vector V in W. So this is U1 V plus lambda U2 V. But because U1 and U2 are in the orthogonal complement, this is equal to 0, and this is also equal to 0. So this inner product is equal to 0. Hence, U1 plus lambda U2 is in the orthogonal complement. And so the orthogonal complement is closed under addition and multiplication by scalar, so it is a subspace of V. It is a subspace of V. Now, very important trick that often it comes in the exercises. Okay. This is the easy way to figure out orthogonal complement of subspace of a given vector space V. Okay. So very important remark. Okay, let's put it as a remark. But it is really, I mean, in solving many exercises, you will be using this trick here. Simple, extremely simple, but important. Now I'm saying, so imagine they give you a subspace of a vector space and they ask you to find the orthogonal complement of it. So the first trick, it is extremely helpful if you have a basis of the vector space W. Sorry, of the subspace W. If you have a basis of the subspace W, then it's very easy for you to figure out a vector space that is orthogonal to all the vectors that is in W. That means, in other words, it is very easy for you to characterize the orthogonal complement. So let me write here. Assume, let's call it B, formed by V1, V2, Vk, is a basis for W. Okay? I just have a subspace and I have a basis. So if the inner product U with Vi is equal to 0 for all I going from 1 to k, so if I have a vector that is orthogonal to all the vector of the basis, if I have a vector that is orthogonal to all the vectors of the basis, then U will be orthogonal to any vector in W. Then U, V will be equal to 0 for all V in W. In fact, why this is true? In fact, so it is, I repeat again, this idea is what? It is enough for me to characterize W orthogonal. It is enough for me to characterize the vectors that are orthogonal to all the vectors in the basis of W. It is enough for me to characterize the vectors that are orthogonal to all the vectors of the basis of W. If I can catch this, if I can characterize the vector U, then automatically it is, I got the W orthogonal. Okay, so let me now here explain why this is true. Okay, now I pick up a random vector in W. Then I know that there exists unique coordinates C1, C2, Ck such that the V is equal linear combination of the vectors of the base. So it's C2, V2 plus Ck, Vk. Okay? Now, then let's take the inner product U with the V. So it's going to be equal U with, instead of V, I have this linear combination, C1, V1 plus Ck, Vk. Okay? And then now I use the property of the inner product. This will be UV1, C1 UV1 plus, keep going till Ck U Vk. Okay? Now, we are saying that U is orthogonal to all the vectors of the basis. So UV1, it's gonna be equal to 0, and U inner product with V2, it's gonna be equal to 0. All of them here gonna be equal to 0, and so the result is gonna be equal to 0, which means that U is orthogonal to V, which means that U is orthogonal to V. That is our statement here. So if you have a vector U that is orthogonal to all the vector in the basis, it will be automatically orthogonal to every vector in the subspace W. Let's do a very simple example. Okay? Okay, example. I'm going to take my big vector space, this with the inner product. I take it to be, for example, R3 with the usual dot product. So my inner product is the usual dot product. Okay? I'm going to take W, for example, to be the subspace of R3 spanned by, let's say, V1 is equal 1, 0, 1, and V2 is, let's say, 0, 1, 0. It's just a simple example, okay? So this is W is a subspace of R3 spanned by these two vectors. So obviously these two vectors are linearly independent, so they form a basis of W. So this is exactly a basis for W, because they are obviously, clearly, they are linearly independent. So, okay, so I have W spanned by those two vectors, and actually these two vectors are linearly independent. They form a basis for W. So W is a subspace spanned by these two vectors. Now the question is, find the orthogonal complement of W. Find the orthogonal complement of W. Okay, so what I'm going to do now, I'm going to go and characterize the vectors U in R3 that are orthogonal to V1 and V2. You must be orthogonal to both at the same time. So I'm going to say, let U X, Y, Z such that U V1 and, don't forget, U inner product V2 equal to 0, equal to 0. This is equivalent to, we are using the dot product, the usual inner product of R3, dot product. So I take the dot product of U with V1 is going to be equal X plus Z equal to 0. And the dot product of U with V2 gives me Y is equal to 0. And now we solve this linear system for X, Y, and Z. So we solve, because I need to characterize the vector U in R3 that are orthogonal to both V1 and V2 at the same time. I end up having a linear system. I'm going to solve it for X, Y, and Z. So we solve this linear system for X, Y, and Z. For X, Y, and Z. Well, it's very clear here. Question number 2 gives you Y is equal to 0. Y is equal to 0. Equation 1 gives me X is equal minus Z. I have no restriction on Z. Z is free. Okay. So I go back and I rewrite my vector U. U will be equal minus Z, 0, Z, which is equal Z times minus 1, 0, 1, Z in R. Okay, so please now pay attention. So what did I prove to you here? Any vector that is orthogonal to both V1 and V2 must be written constant times the vector minus 1, 0, 1, minus 1, 0, 1. Okay, but here, I told you here that if you catch the vectors that are orthogonal to the vectors of the basis, in our case here, V1 and V2, you will have that vector is orthogonal to any other vector inside your vector subspace W. So now, I know that any vector that is going to be written under this form, constant times minus 1, 0, 1, will be orthogonal to every vector inside W. I repeat, any vector written under this form, a constant, a scalar times the vector minus 1, 0, 1, will be orthogonal to every vector in W. That means the orthogonal complement, the vector inside the W per orthogonal complement, must look under this form. And so the orthogonal complement is the span of minus 1, 0, 1. Hence, the orthogonal complement is the span of this vector minus 1, 0, 1. Okay. So this is how you got the orthogonal complement. It's very simple method. The argument is very clear here, simple. So each time they ask you to compute the orthogonal complement of a subspace, I'm saying it is extremely easy to go and check for a basis for this subspace. If you have a basis of the subspace, then you need to come up with a vector that is orthogonal to all the vectors in the basis, to all the vector in the base. Then you will catch the orthogonal complement. Now, I will go for another important fact, but this one extremely important, very important. And I relate it to the previous example we have done here. Okay, now, let's go back to this previous example. This is going to be our motivation. What is the dimension of W here? So W, we said, is the subspace of R3 spanned by these two vectors. These two vectors are linearly independent. They form a basis. And so it's obviously dimension of W is equal to 2 in this case. And now here, if you look at the dimension of the orthogonal complement, what do you get? You get 1. If you sum the dimension of W plus the dimension of the orthogonal complement, I got 2 plus 1, it's 3. It's equal to the dimension of the whole vector space. And this will be always the case if W is a subspace of an inner product vector space V. And let's assume, let's assume that dimension of the big vector space is finite. Okay, so V has a dimension, let's say n. And if W is a subspace of V, of this inner product V, okay, then the dimension of W plus the dimension of the orthogonal complement of W will be always equal to the dimension of the big vector space V. So let's write it here. So basically here, before even I solve the problem, I know that the W perp must be spanned by only one vector because the dimension of W is 2 and I'm inside the vector space of dimension 3, then the orthogonal complement must have a dimension 1. So before even solving this, I know that my W orthogonal, the orthogonal complement must be spanned by only one vector. So assume V is such that I have an inner product is such that dimension of V is equal, let's say, n. For any subspace W, for any subspace W of V, we have dimension of W plus dimension of the orthogonal complement is equal to the dimension of the big vector space N. Please never forget this one. Okay, never forget this one. Okay, like for example, very easy here I'm gonna put it as a remark because there is the easy case. What is the orthogonal complement of the big vector space V itself? What is the orthogonal complement of the big vector space V itself? There is only one vector inside V that is going to be orthogonal to all the vectors in V. There is only one vector. It's the O vector. So I know that V orthogonal is the O. So that means the orthogonal complement of the big vector space is the trivial subspace that is containing only the O vector. Now, if you sum dimension of V plus dimension of V orthogonal, well, the dimension of the trivial vector space is equal to 0, then this guy is equal to 0. So I got dimension of V. It's going to be n. We denote it by n. So this is always satisfied even if you take the big vector space V itself, because the orthogonal complement for V is the trivial subspace O of V. The trivial one contains only the O vector, because only the O vector is orthogonal. There is only one vector, the O vector, that is orthogonal to all the other vectors in the big vector space. In the big vector space. Okay. Let's do another example. Okay. Any one, I'm gonna just take, let's do 48, one example from exercise 48, okay? So let's say, okay, so how many vectors vectors here, 5. Okay. So let's say I have capital V is R4 and W, and with the inner product, the classical dot product in R4. I have W is the span of the following two vectors. V1 is equal to 3, 0, 1, minus 2, and V2 is equal to minus 1, minus 2, minus 2, and 1. Okay? And the question is find the orthogonal complement. Okay? So I have a subspace of R4 spanned by these two vectors. Obviously, these two vectors are linearly independent, so they form a basis for W. This is a basis for W. So I know that the dimension of W here is equal to 2. Okay, so W is a subspace of R4 spanned by these two vectors. Obviously, these two vectors are linearly independent. They form a basis for W, so dimension of W is equal to 2. Now, the question is to find the orthogonal complement. I'm going to follow the same method here. However, in advance, I know that the orthogonal complement must be spanned by two vectors linearly independent. So the dimension of the orthogonal complement must be equal to 2, because 2 plus 2 gives me the dimension of the big vector space 4. Okay, so I know that in my calculation during this process here, if I end up having more than 2 vectors, that means I made a mistake. More or less, that means I made a mistake. I have to go back and check again. So now how to find the W orthogonal? Well, again, I'm going to pick up a random vector in R4 and characterize those vectors that are orthogonal to both V1 and V2 at the same time. So I'm going to say let U is equal X, Y, Z, and W such that U V1 is equal to 0 and U V2 is equal to 0. This is equivalent to say, so I have the usual dot product here, the inner product is the usual dot product, so E3X plus Z minus 2W is equal to 0, and minus X minus 2Y plus minus 2Z plus W is equal to 0. Okay, so for example, what can I do here? I can write number 1 gives me, okay, the first equation gives me X is equal minus 1/3 Z plus 2/3 W, okay? And I substitute this one in the second equation. That gives me Y is gonna be equal 1/2 times the minus X, which is 1/3 of Z minus 2/3 of W, okay? Minus Z plus W. So let's clean up this one, which is equal. So how many? So here I have 1/6 minus 1 minus 5/6 Z. And here I got minus 1/3 plus 1, it's plus 2/3 of W. So the Y, bring it here, you divide by 1/2, you have the minus X is here. This guy becomes minus Z, and this guy becomes 1/2W, sorry. Okay. Plus 1/2W. So again, so I got minus 1/3 plus 1/2, so I got 3 minus 2, 1/6, and the other is minus 5/6. So minus 5/6Z plus 1/6W. And no restriction on Z and W. Z and W are free. Are free. Okay, so I go back and rewrite now my vector u. Thus, u is equal to, well, instead of x, I have minus 1/3 z plus 2/3 w. Instead of y, I have minus 5/6 z plus 1/6 w, 1/6 w, and then I have z and I have w. Okay, so it's gonna be equal z times the vector minus 1/3 minus 5/6, 1 and 0, plus w times 2/3, 1/6, 0 and 1, and zw in R. So basically, every vector that is orthogonal to any vector in W, because if it is orthogonal to the vectors in the base, to the vector of the basis, this vector u will be orthogonal to every vector in W, must be a linear combination of these two vectors. That tells me, hence, the orthogonal complement is just the span of these two vectors, is the span of these two vectors, minus 1/3, minus 5/6, 1, 0, and 2/3, 1/6, 0, and 1. Okay, obviously these two vectors are linearly independent, and we can see that the dimension of the orthogonal complement is equal also to 2. So the dimension of the orthogonal complement is equal to 2, spanned by two vectors that are linearly independent. This is why the dimension 2. And again, you can check here. You can check that the dimension of W, which is equal to 2, plus the dimension of the orthogonal complement, which is equal to 2, is equal to the dimension of the big vector space R4, which is equal to 4. Okay, so I'll stop here, and other videos about the Gram-Schmidt process, and will be posted by Dr. Zia. Thank you.